Okay, I want to talk about closed systems. And these are systems where the mass can't move in or out of the system. Two main types of closed systems we talk about we normally encounter, I should say, are rigid tanks. And rigid tank means what? That the volume doesn't change, so V1 equals V2. And of course in industry we try to make our tanks rigid so that they don't change volume. And we have piston cylinder type arrangements where the volume can change. So you'll find a lot of these types of problems, either one where the volume doesn't change or the volume doesn't change, but in either case the mass is contained in the system, so M1 equals M2, or we'll just call it M. M is the same throughout the closed system. And for this video I want to talk primarily about, in fact exclusively, about an ideal gas. And the example I'll use is air, and I'm going to assume constant Cp. In other words, I'm going to neglect the change in Cp or Cv on changes in temperature. So Cv we're going to take to be equal to 0.24 BTUs per pound mass. I'm sorry, Cp 0.24 BTUs per pound mass, and Cv equal to 0.17 BTUs per pound mass. You can convince yourself that this relationship holds because you recall Cp minus Cv equals Ru over molecular weight. That is the universal gas constant over the molecular weight to get it into mass units from molar units. I'd suggest you just stop right now and just confirm that this is true for these two values of Cp and Cv. Good practice. Let's look at three cases of closed systems. The first will be constant pressure, constant pressure expansion in a piston cylinder arrangement. We call constant pressure, by the way, that's isobaric. Iso meaning constant, baric meaning pressure. Constant temperature, that's isothermal. And adiabatic. And you recall adiabatic means Q equals 0. I'm going to look at those three cases for piston cylinder expansion of a gas. And also I'd like to look at constant volume process. Constant volume, what we call that isochoric. You rarely hear that word, but that's the term for constant volume. Okay, we're going to define the problem for expansion. Let's make this state 1, state 1 here, and state 2 here. And we'll suppose that the volume at 2 is twice the volume at 1, or let's suppose we started with 10 feet cubed here, and we went to 20 feet cubed. And we'll have the same initial starting place for all three of these expansion problems and expand to the same double the volume. So let's make this initial pressure in all cases P1 equals 50 psia. And we'll make the initial temperature T1 is 1000 degrees Rankine. And from that we can calculate the mass. So the mass is equal to PV times the molecular weight over RT. And that comes out to, let's see, and I'd encourage you to, once I get these numbers up, to stop the video and convince yourself that the units here are correct. That's, let's see, 10 feet cubed. Let's make it 50 psi times 10 feet cubed times the molecular weight of air is 29 pounds per pound mole, divided by R, 10.73 for the units we're using, and T is 1,000. That gives us an initial mass of 1.35 pound mass. So 1.35 pounds we have in there to start. Now, we want to find from the energy balance, remember N, we're going to assume that we had to put some heat into this. So we put a little flame underneath it, put some heat into this, and we expand it so there's heat going in, Q in, and let's take work out. So we're doing work by lifting the piston, heat in, and work out. So the energy balance is in equals out plus accumulated, or Q in. Let's make that Q in orange. Q in equals W out plus delta U. There's our energy balance. In equals out plus accumulated. Next we'll solve for the work in, or the work out rather. And you recall work out equals the integral of P dV. This is fortunate in this case because pressure is a constant, and we can move it out in front of the integral, and we have P, the integral of dV, or P times V2 minus V1. So we have P, which is 50 psi, times V2 minus V1. Remember, the volume doubled is the statement of our problem. 20 minus 10, V2 minus V1, are 50 psi times a change of 10 feet cubed. 500 psi feet cubed times 0.185 BTUs per psi feet cubed, psi foot cubed. And that comes out to, approximately 92.5 BTUs. So let's go back and look at our work is 92.5. And now to find the amount of heat that we have to put in to this system, we have to know how much the delta U was. Well, in this case, the temperature changed because we have the restriction that P2 V2 equals nRT2. So I'll go down here and do that calculation to find T2. We know that T1, let's say P1 V1 equals nRT1. We know that P2 V2 equals nRT2. You see, if we divide one equation by the other, the n's cancel, the r's cancel, and we have T2 equals T1 times V2 over V1, and that times P2 over P1. And of course, since it's constant pressure process, P2 equals P1, that cancels out. We know that V2 equals 2V1, so this becomes 2, or T2 equals 2T1 equals 2,000 degrees Rankine. Now you always have to be very careful and make sure you're in absolute temperature when you're doing these calculations. So we have then delta U. Delta U is equal to m times the specific delta U, and I'll use a lowercase for that, and m was 1.35. Delta U for an ideal gas is CV delta T, so CV is 0.17, and delta T was 2,000 minus 1,000, or we come up with the delta U is equal to 229, about 229.5 BTUs. And again, I'd encourage you to stop, convince yourself that the units work out in this problem. So for this first scenario where we have the pressure constant, we have Q equals 92.5 plus delta U, which is 229.5, gives us a QN of 322 BTUs. So if the question was, find how much heat is needed to double the volume in a constant pressure process, starting from our initial conditions, the answer is 322 BTUs. Okay, now let's look at the isothermal case. Isothermal, where T1 equals 1,000, T2 also equals 1,000. And we'll take the same case where we started at 50 psi. P1 equals 50. And the volume is doubled from 10 feet cubed to 20 feet cubed. Now in this case, again, we have the energy balance. Work in, QN equals work out, because we're expanding, plus delta U. Now, if it's isothermal and delta T is 0, and it's an ideal gas, then delta U is 0. So it's a fairly simple conclusion that QN is equal to W out. Now, of course, we're assuming all along that the work we get is due to the expansion of the gas, where the pressure internal is the pressure external. So I'm going to put in little green here, indicating that we have a frictionless sliding of this piston up and down the cylinder, and that we do it slowly enough so that the gas doesn't swirl back on itself and cause internal friction, so that we get all the work that we possibly can. And that's a common thread that we'll get to when we talk about the second law. But I want to point that out here. Anyway, going back to the idea, we have an isothermal process. T is constant, so delta U is equal to 0. Qn equals W out. So all we need to do is solve for W. Remember, W equals the integral of P dV. Here, however, the pressure is changing. And since the pressure is changing, we have to be careful how we integrate it. If it's changing with respect to V, we can't take it outside of the integral. But we can solve for pressure from the ideal gas equation. P equals m over molecular weight RU T over V. Plug that in here, and we have work is equal to the integral of m R T over molecular weight, integral of all that, dV over V. And the nice thing is that T is constant, because we're doing this for an isothermal process. So we can take T outside of the integral. We can take R outside, it's constant, M outside, and molecular weight can go outside of the integral. So we wind up with m RU T over molecular weight, the integral of dV over V. Now we have dV over V is the only thing inside the integral, and that's a simple integration that equals to ln of V. So I'll go down a little bit and write MRUT over molecular weight. And you'll recognize, by the way, a shortcut to that, depending on the variables that you had to find, is that's P1 V1, because T is constant. That's P1 V1, the integral of dV over V, and this integral is ln of V2 minus ln of V1, or with little algebraic manipulation you have ln of V2 over V1. So the work out in this case is equal to P1 V1, which was 50 psi, times V1, 10 feet cubed. And the volume doubled, so that's ln of V2 over V1 is 20 over 10, or ln of 2. And this comes to, oh, let's multiply that times 0.185 BTUs per PSI feet cubed. And that comes to 64.1 BTUs. So we'll go up here to where we had our energy balance, and we have Qin equals W out, and they're both 64.1 BTUs. So that takes care of the situation where we have constant temperature or an isothermal process. So finally, let's say we put in Q 62.4, and we got work out also 62.4. Let's move on now and talk about the adiabatic process. Now again, we're looking at the adiabatic process, so we have insulation indicated in pink around the cylinder, so that our energy balance becomes Q is 0, or 0, since it's adiabatic, 0 equals W out plus delta U. And otherwise, the process is going from 10 feet cubed to 20 feet cubed. And as it expands, the temperature has to drop because we're taking work out, but we're not putting any heat in, so the temperature will drop to accommodate that as per the energy balance. Again, we want this to be frictionless, and we want it to happen slowly. In order to happen slowly, we have to balance the internal pressure. Since the temperature's falling and the volume is increasing, the pressure is going to drop as well. So we have to slowly remove the load from this piston in such a way that we balance the pressure against the expanding gas. So as the temperature and the pressure of the gas drops, we have to balance the load such that the internal pressure is equal to the external pressure. Now we have the integral of PdV is equal to the work out. But since for a small amount of work we also have the CV dt, we have to do this in an integral fashion. CV dt, a small change in the internal energy. We'll have to integrate that as well, add those up, and it's equal to 0. Now for the ideal gas, we have P, as we saw in the section before, is equal to m over molecular weight RUT dV over V plus CV dt equals 0 for a differential amount of it. And we can rearrange that somewhat to get, before we do, we need an M in there as well in front of the CV, because that's the total internal energy change, and this is the total work. So we rearrange that again, rearrange that a little bit, cancel out the M's on both sides, and with some algebra we can show that dt over T equals minus RU over molecular weight divided by CV times dV over V. Now we can integrate both sides and wind up with a little more algebra, and I suggest you prove this to yourself at home, that T2 equals T1 times V1 over V2 raised to the RU over molecular weight over CV. So now let's plug in the numbers and find T2. Give ourselves some room. T2 equals T1, 1000, times V1 over V2, 10 over 20, raised to the RU. Now we have to be careful with the units of the gas constant. Let's put it into 1.987. That's BTUs per pound mole degree Rankine. Divide that by the molecular weight 29, all divided by CV 0.17. Got to make sure we have consistent units. That comes up to T2 equals to 756 Rankine. About 300 degrees Fahrenheit, a little under. And so we have T2. T2 is 756, so delta U is equal to mCV delta T, or delta U is equal to 1.35 pounds times CV's 0.17 times 756 minus 1000, comes up to a delta U of minus 55 BTUs, 55.0 BTUs. Put that back into our energy balance, and we have Wn plus minus 55 equals 0. So Wn therefore must be plus 55, and out of this process we get a work of 55 BTUs. So now we've looked at the what we call adiabatic case, and this is going to have implications when we get to the second law. We've looked at adiabatic and, let's say, frictionless, in that we did it very slowly so that there was no internal friction in the gas, and we lubricated the sides of the piston so that of the cylinder so that there's no friction there, and we came up with a work output of 55 BTUs. The last thing I want to look at is a constant volume process, which is essentially a tank. Suppose we welded the piston shut in that cylinder, and we'd have essentially a tank. Piston can't go up or down. So V1 equals V2, and what's that tell you about the energy balance? N, let's say we put Q in, put a little flame under it again. Qn equals out, work out, plus delta U, and in this case it's kind of trivial because what's the work out? The integral of P dV, but in this case the volume doesn't change. dV is 0, so the work out is 0. This whole thing goes to 0, and we have Qn equals delta U. So really we're not getting any work. You can have these kinds of problems if you want to know, for instance, if you add a certain amount of heat, what will happen to the pressure of an ideal gas. And let's take a look at that. How much heat would it take to, say, double the pressure such that P equals 100? Well, we know that P2 V2 over T2, solving the ideal gas equation, is equal to P1 V1 over T1 for a constant volume process. The volumes will cancel out, and then we have T2 is equal to T1 P2 over P1, and we know that, or let's say P2 over P1 is equal to 2. If we're doubling the pressure, then T2 is equal to 1000 degrees Rankine, and that the heat that we put in by the energy balance, Qn, is simply delta U, which is CV mass, CV delta T, and delta T is 2000, because it doubled, minus 1000 that we started with, or 1.35. Let's solve that. 1.35 times 0.17 times 1000.